So now let's see how to model an initial position instead of an initial velocity. So let's just be clear on what the solution to this looks like. The ordinary way of saying it would be y of t is equal to y naught cosine omega t. But to extend it to something that has meaning on all of r, and it has this property of doing nothing and suddenly going to an initial position, which is what I want to model, we're going to multiply that by h of t. Okay, so how is that going to show up as a distribution? Okay, well, let's take this guy and let's plug it in to my double prime plus m omega squared y, and then see what happens when we hit that against the test function phi. Okay. Now, clearly, the alternate version of our initial conditions still works. Just a long time ago, nothing was happening, and then suddenly something happens here. And then after that, really nothing interesting happens. It should be whatever this mysterious distribution is, whatever the right-hand side is, it should be something that's supported at 0, because afterwards, it's just, this really should be giving me essentially 0. So, and we'll see that. Okay, so let's just go ahead and do that calculation. And so that's going to be m integral of y double prime. Well, you know what? I'm just going to go ahead and, well, by definition, if y is thought of as a distribution, it's y of phi double prime. Just skipping a couple steps, but from the stuff we were doing in the last video. It's super similar. And then here, there's nothing interesting going on. It's just y of t, phi of t. Okay. And let's see what happens when we do our the magic of integration by parts. So let me see if I can keep the picture. Okay, so this is going to go up here. Alrighty, so now, oh yeah, so first of all, that's just from 0. That's still true, because it's just, that's what the h of t does. Okay, and then I'm going to do integration by parts on this guy, my of t, phi prime of t, 0 to infinity, minus m integral 0 to infinity y prime of t phi prime of t. One derivative has moved over, dt. Okay, and then plus the uninteresting part, where nothing really needs to go on until the end. Okay, all right. Now here's what's different about this new situation. Y of t, this is still, of course, going to die, but the compact support of phi. But y of 0 is not 0. And of course, there's a minus hidden in the evaluation bar there. And we get minus m y naught phi prime of 0. Oops, sorry. Put it in the wrong place. Give enough room. Minus m y naught phi prime of 0. So that's where the y naught's coming in. Okay. And then minus, this stuff is really unchanged. Okay. Same stuff. Okay, and so that, oh yeah, so let's see, phi prime of 0 with a minus, that's my naught, that's exactly by definition what delta prime does to phi. Aha, so we've got a delta prime going on here. This is the first place where this has really come in as a practical gadget. Okay, now what else we need to do? We still need to do one more integration by parts here, and so we're going to get minus m y prime of t phi of t from 0 to infinity, plus, and then the integral, and then I'm going to be able to put everything else together. Now it's my double prime plus m omega squared y. Now I am doing the homogeneous version. The only forcing here is whatever funky distribution is doing this thing, and there's no other forcing. So this does vanish, unlike in the previous one where it was a big F, but that really just does vanish here, just for simplicity. Okay. And, oh, sorry, so it's all this together. And this guy, because I've been specializing to the case where y prime is equal to 0, this always dies, y prime of 0 is 0, for simplicity. And you just get my naught delta prime on phi. All right, so the simple answer, the summary, is that it's the solution. This y is the solution to this problem. My double prime plus m omega squared y is m y naught delta prime. And to make it unique, y of minus infinity and y prime of minus infinity are 0. That is an alternate way of thinking about a initial value problem with initial position. You start out with the homogeneous case, 0, 0, nothing's happening, and then you do something to sort of teleport it. So that might sound a little weird. Are we teleporting it? Okay. I think it feels a little bit less physically reasonable than hitting it with a hammer. But hitting it with a hammer with an infinitely concentrated impulse isn't really what happens. It's just an idealization. So hopefully we can see this as an idealization, a very cool and simple idealization, once we get used to the delta prime and everything, of a realistic situation. If we can't see it that way, it isn't, I don't think it's terribly useful. It's certainly not the kind of useful that I want to focus on here. Okay. But as I say in the, well, here's one thing I want to point out. The most simple analogous version of this is if I have a function that's going like here, and then bam, just goes up and does the teleport and then does nothing interesting. Well, we know what that function is. That's h of t. Okay. And basically, the most important thing that happened here was the second derivative. This was just not terribly important qualitatively. And in particular, physically, it doesn't have a lot of impact right when, as you do this, whatever this extreme behavior right at 0, the spring doesn't have a whole lot of time to react to that. And we'll talk about that even a little bit more explicitly in a minute. So basically, it's taking h of t and taking two derivatives. And that's exactly where we first saw delta prime coming up. That's delta prime, because one derivative, h prime, is just delta. Okay, so we're basically taking a second derivative of a jump, and we're getting delta prime. I don't think that quite really explains or gives you much intuition about it yet. Okay, so it's so far we see that delta prime comes in as a way to, it's some sort of thing that teleports something, and it's also the second derivative of a jump. What's going on with that? And one good way to do that is look at the other perspective on distributions, not the one we're using as a definition in this formal definition of acting on test functions. We want to think of it as, so we're going to have like this funky, well, let's say this situation. We're going to look at this situation with this forcing function and this y as a limit of ordinary, sort of an ordinary ODE situation with ordinary functions. Okay, so that's what 5 is about. So let's start that out. So very much like going back to even the first handout, we'll say f sub epsilon of t, and we'll have these nice way to the left homogeneous initial conditions. Those are 0. Okay, and f sub epsilon, well, let me draw the picture. Okay, what we're going to do, what do we want to do? To quickly move this function, if you want to look at y first, what we really want is, if we don't have to do it in time 0, we want it to quickly accelerate upwards and then quickly decelerate, ending up at y naught, all happening in a short time, epsilon or 2 epsilon or something like that, and then then the spring takes over and does its usual thing. Okay, so we'd like to do some very quick acceleration and then deceleration, so it ends up with a non-zero initial position, or well, position at like epsilon or 2 epsilon or something like that, and 0 initial velocity. And as that shrinks, it just gets faster and faster and faster. It starts to look like teleporting. And that's just a matter of really scale. If it happened really quick in the blink of an eye, you're going to model it as instantaneous. It's a very common thing, even though you know secretly, okay, maybe it happened in a millisecond or a microsecond or something like that. So here's the proposal as to the function that's going to do that. Okay, we're going to have a rectangular pulse, and I'm going to start it. I'm actually going to make it more symmetrical. I'm going to start it a little bit ahead of time. It's going to start at minus 2 epsilon and end up at 2 epsilon. Okay, so that's what the y is going to want to look like. The f, the claim is we just started with a rectangular pulse, constant acceleration upward, and then decelerate symmetrically. Ooh, these should be dotted lines. And it's going to be easier to deal with some of the algebra and connect it with other stuff if that's 2 epsilon and that's 2 epsilon. So we're going to have a rectangular pulse from 2 epsilon to 0, and then minus a rectangular pulse from 0 to 2 epsilon. And then I claim that this is the right factor. And it took me a while to get the right factor because I lost factor of 2 for some stupid reason. Okay. So that's the situation. I claim that this kind of pulse, hammer one way and then hammer the other, is going to give some constant acceleration, then constant acceleration, and then let the spring take over. Now, we do want to make sure, as soon as you start hitting it, the spring is going to be acting. But if this epsilon is really small, then this is going to be a really big constant, a really big strength for that force. And so compared to that, the spring is not able to do much. And so in this small time, we can ignore the action of the spring, basically. Okay, so there's another way to write this. What we found is that it's even better to write this for solving purposes in terms of steps. This is a step at minus 2 epsilon, then minus twice a step at 0. So step up, then step double down, and then step up again to kill the down at 2 epsilon. Okay, and we use the miracle of linearity because we're focusing on linear ODEs here, and we just look up the solution from previously. It's the m cancels, it's 1 over m omega squared was the factor, the 4 stays there. And instead of an m on top, we get an omega squared on the bottom. And then what happened when you hit it with a step function was we got a 1 minus cosine, because that has the right behavior of nothing, 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 then gradually starting up, and then oscillating around the new normal when you've got a fixed non-zero forcing function. And this is cosine omega of t plus 2 epsilon to be shifted to the right place, and then times h minus 2 epsilon of t. I just realized there's a typo in the solutions that I'm looking at. That should be at minus 2 epsilon. I'll try and fix it later. All right, and then just the same exact thing, but not shifted and with the appropriate factors. H of t, and then plus 1 minus cosine h2 epsilon of t. Boom. Okay. Looks kind of complicated. Okay, but the main thing is what we're interested in what happens when epsilon goes to 0. Okay, this is problem 6. The limit as epsilon goes to 0 of y epsilon of t. Okay, what happens with that? Well, this is a nice kind of limit to take. You've got functions with epsilons in them, and you're dividing by epsilon squared, and we're going to take the limit. We're basically taking a second derivative here. It's probably easier to think about in terms of L'Hopital's rule, and we'll see that comes out. So the y naught over 4 omega squared comes out as a constant. And then, okay, so one important observation is that, I forgot to make one observation first, sort of graphical observation. Okay, we know what's going on before t equals 0, nothing, okay? Then there's this short region up to, before minus 2 epsilon, because it's symmetrical. We've got some question marks in here, okay? After that is what we're really sort of interested in. What happens after we do this funky thing, this weird double pulse in the middle? We really are focusing on what's happening after 2 epsilon. And since we're taking epsilon smaller and smaller and smaller, that's going to encompass any t greater than 0 that we want. Okay, t less than 0 is clear. As this minus 2 epsilon gets smaller and smaller and smaller, nothing's ever happening before minus 2 epsilon. Okay, so before t equals 0, it's 0, is what we want to have happen. And then afterwards, these guys are all equal to 1. Okay, so for any t greater than 0, just crank the epsilon down enough so that these are all turned on. And so those go away. Okay, and now we're going to do a L'Hopital's rule calculation. Well, actually, let me just use that alone. Okay, we're just going to delete the h's. Oh, and once we delete the h's, 1 minus 2 plus 1 cancels out. And so here's what we get. Plus 2 cosine omega t, and then see if I can squeeze it in here, minus cosine omega t minus 2 epsilon. There we go. Okay, so now we use L'Hopital's rule twice. Okay, got over the 4 omega squared. Okay, oh, I just was talking, there's a 1 over epsilon squared here, which is really crucial. Okay, when we take the derivative of that, it becomes 1 over 2 epsilon. Okay, see if we can fit it all in here. Now, remember, we're taking the derivative with respect to epsilon. We're thinking of a fixed t value and trying to say, what does this function look like when epsilon goes to 0? Not anything about t. And omega is, of course, constant as well. So the minus cosine turns into a sine of the same argument. And the factor that comes out is a 2 omega. Okay, and then here, this is convenient. This doesn't have an epsilon in it, so it just dies. And then this is going to turn into a minus. Now, the minus cosine would turn into a plus sign, but then you get a minus 2 omega. So it's going to be minus 2 omega sine omega t minus 2 epsilon. Okay, use L'Hopital's rule once again. And we're getting, this is going to be, well, the 2's cancel. So these 2's cancel. Okay, and then we're going to get, we have the omega already, and we're going to get another 2 omega. So it's 2 omega squared. Back to cosine with a plus sign. And then this is going to be plus, again, 2 omega squared. And now there's no epsilon in the denominator. I need to keep writing my limit as epsilon goes to 0. That's a mistake my calculus students always make. Okay, and now I can just set epsilon equal to 0. And I get a little cancellation here. The omega squared cancel out, and I get, there's 2 of these, so that's 4, cancels the 4. And so I just get y naught cosine omega t. And of course that was true for any t greater than 0. And of course it was equal to 0 if t less than 0. And that's exactly what we wanted to see. Okay. So let's just make clear the upshot of that. Okay. It says that if I hit, let me just remind you of what's going on. This is kind of long, isn't it? Wow. If I hit with the forcing function looks like this, minus 2 epsilon, 2 epsilon, then the y looks like this, some constant acceleration or to a very good approximation, and then constant acceleration to a very good approximation. And this is taking into account the actual effect of the spring even in that time period, but it doesn't really have much of an effect. And then, boom, and then it's done forcing, and it just goes on its merry way as a cosine. And as epsilon goes to 0, this starts to look more and more like teleportation. And it just starts to look like discontinuous and then cosine. Okay, and that's good. So even though it's a little long, let me continue with 7 just real quick, because I actually have almost said all of 7. It's the thinking like a physicist idea. Okay, that if you look at the acceleration of this mass that's on a spring, if you just solve the equation or differential equation for that, for y double prime, you get that it's the force that you're putting on it divided by m minus omega squared y, And I've talked already about how we don't expect, and this is the tiny, not rigorous part of this version of the argument, if we don't expect y to teleport to an infinite value or a huge value, if it's going to around y naught, okay, then that's kind of bounded. And the f epsilons, as we take epsilon smaller and smaller and smaller, these are getting to be incredibly huge forces. And so we just neglect that, okay. And then we're just going to get exactly just constant acceleration. And so as this, I shouldn't have erased this picture. I've got an acceleration of, it's going to be y naught over 4 epsilon squared is the acceleration. Then y of 0, I start out at minus 2 epsilon, and I accelerate with this acceleration for 2 epsilon time, 1/2 times acceleration times t squared, 1/2 y naught over 4 epsilon squared times the quantity 2 epsilon squared. The 4 cancels out, and I'm at y naught over 2. So there's my forcing function. Actually, this is a graph of the acceleration now. And the y has undergone constant acceleration. It gets me exactly halfway up to where I want to do. And then by symmetry, I just decelerate, getting me back exactly at 0 velocity, but twice as high up to height y naught. And that's the idea for 7. That as long as we can convince ourselves to ignore this, it's really pretty convincing that this is not an unphysical thing to do. It's just weird that it happens so fast that you blink your eye and it looks like the object is teleported.